Hello everybody, I'll talk today continuing my last session about MRI basic physics. Last session we talked together about transverse and longitudinal magnetization. Today we'll continue our discussion about basics of MRI. Uh, Today we will continue talking about MRI basics, and we'll continue after longitudinal and transverse magnetization. We will talk about MRI signal and T1 and T2 and the proton density sequences in MRI. But let us talk again and briefly about what happened before. When we place the protons outside the main magnetic field, we'll find that the protons are randomly distributed. As you see, each proton is aligned toward a certain direction, and another proton toward another direction. So each one has a magnetic property. So two magnetic force in opposite directions, so neglect each other. So the protons here random distributions inside the patient. So the net magnetization here will be zero. But here, when we place the patient or place this sample of protons inside the main magnet, what will happen to the protons? We will find that protons are lined up and another protons are lined down, lined up parallel with the lines of the magnetic field. Where the lines of the magnetic field in this direction, in that direction, from south to north pole, and the protons which are aligned up have a greater number than protons aligned down. The difference between number of protons aligned up and down is 7 protons per million of protons, 7 protons per million. So each proton lined up have another proton lined down, so two protons, two magnetic force in opposite direction neglect each other. So the difference between, or the net result of this alignment will be 7 proton per million. So this 7 proton will be the source of signal, we will use these protons to be excited with radio frequency pulse coming from outside from our coil to excite it, and after a certain time we will switch off our radio frequency source of radio frequency pulse, and protons relax again, and radio frequency pulse coming out and received by radio frequency coil to translate it to form image. Okay, as we told before, that the protons are aligned with the main magnetic field, which when applying the external magnetic field, and acquire precessional frequency or precessional motion process around the main magnetic field. This precession frequency or precession motion depend on the external magnetic force, where when the external magnetic force is higher, so the precession frequency is higher as well. So there is a direct relation between the precession frequency and the external magnetic force, according to Larmor equation. So now it's important to know the precessional frequency. Why it's important to know the precessional frequency? Because if we know the precession frequency of protons, it's easy to excite it. Because when we, as I told you before, that if you have here two cars or two drivers moving with the same speed, if you want to transfer energy, it's important to transfer the energy, okay, from a car moving with the same speed with another car. Okay, if the so now you can transfer energy like protons. If we know the speed of precession or the precession frequency of protons inside the patient, and we want to transfer energy, we have to transfer energy with frequency, okay, with a certain frequency of with the same frequency. So you have to know the precession frequency of proton. But if there is a difference between the frequency of proton inside the patient and the radio frequency pulse, okay, coming from the radio frequency coil, if there is so you can't transfer energy, the energy will be lost in this case. So it's important to transfer energy or to give a radio frequency pulse from radio frequency coil has the same frequency of protons inside the magnet. Okay, and as we discussed before, as I said before, that the radio frequency pulse, the angular frequency, which is the precession frequency of proton, depends on the external magnetic field, which is angular frequency equal to gyromagnetic ratio times times external magnetic force, which is according to the machine maybe 1 Tesla or 0.5 Tesla or 1.5 or 3 and so on. Okay, so according to the value of magnetic field, thermal frequency increase. Okay, this constant is called gyromagnetic ratio, which is specific for H material, H material. Okay, and for hydrogen we will find that thermal frequency at 1 Tesla, this is B naught, okay, 42.5, and for fluorine 40.0, and phosphorus 17.2, and sodium. So now why hydrogen is higher thermal frequency on applying 1 Tesla? Because hydrogen has one proton, has higher magnetic probability, has higher sensitivity, so thermal frequency or precession frequency will be higher than other atoms. So now on applying 1 Tesla, the protons inside the hydrogen atom will precess with speed or with frequency 42.5 megahertz. If we increase the higher magnetic field on applying higher magnetic field like 1.5 Tesla, the thermal frequency will be increased to around 62 megahertz. So increasing the external magnetic field will cause increasing the thermal frequency of atoms. Okay, but because we are interested and we concerned with hydrogen atom, so we will image only the hydrogen atom inside our bodies. So now the protons in random distribution, as you see, the protons inside our bodies in random distribution. On applying the external magnetic field, the proton align with the external magnetic field lines in the direction, maybe in opposite direction or in the same direction of external magnetic field. Okay, and acquire the precession motion. Okay, but all protons in the during applying the external magnetic field, precess with the same frequency, but not in the same phase. To understand, not in the same phase, like here. On applying the external magnetic field, now the external magnetic field, this is the protons aligned, some aligned up and some aligned down, as you see. All of them precess in the same frequency. The frequency of this proton like this. Okay, so all protons now precess with the same frequency, but the only difference that the time of precession here, you will find this one is all of them out of phase. Out of phase means that not all protons start together and stop together. No, you will find that one proton start at certain time and another proton start next to this proton, and so on. So all protons here are out of phase, not in the same phase, not starting together and not stopping together. Okay, not moving with time, not moving with the same time. Okay, so now all of them have the same precession frequency, but out of phase. This is very important information, because out of phase means that summation, this proton, each proton here has act like tiny magnet, tiny magnet. So each one has a magnetic property, adding magnetic field, adding magnetization to the main magnetic field, adding magnetization to the net magnetic field. So if these protons are in phase, that means all of them moving together. Okay, start and end together. Okay, so now the net magnetization will be higher. The net magnetization of protons will be higher because all of them are in phase. So out of phase, causing the net magnetization of protons will be less. But these protons which are aligned with the main magnetic field, adding magnetization, increasing the magnetization of the magnetic field. But if you want to record the magnetization, this magnetization coming out from proton, you can do this because the protons here precess. The protons here adding magnetization to the main magnetic field, so you can differentiate between the magnetization coming out from protons and the magnetization coming out from the main magnetic field, because all of them in the same direction. So how can I differentiate between the protons, the magnetization coming out from protons and magnetization coming out from the main magnetic field? You have to move these protons in another direction. You have to move these protons in another direction, not in Z direction, but maybe in XY direction, as I said last time. Okay, so this is the reason why we are using radio frequency pulse with the same frequency of protons to excite it, to convert it from the Z direction to the XY direction, okay. So now we will apply radio frequency pulse. As we said before, we will represent the proton with this red arrow, and the proton now precesses around the axis of the main magnetic field, okay. And now all protons out of phase. You will find that all of them out of phases, as you see, some protons up and the protons down, as you see. When applying a radio frequency pulse, what will happen to the protons? Okay, the protons now, all of them up, each one in a certain direction. We'll find another proton in another direction, so neglect each other. So I'll find the resultant, or the net result of the difference between protons up and down will be some protons up. This proton I'll depend on it on getting on imaging, depend on imaging, okay, depend on them during imaging process. So now the proton process around itself, you will find here protons, each one represented by arrow, and another proton in the other direction, to opposite force, neglect each other, okay, as you see, and to other proton, 1/3, okay, neglect each other. So the remaining proton, I'll use the remaining proton to get the image, or to be excited to get the image finally, okay. This is the precession frequency, as I said before, okay. Here all protons out of phase and in the Z direction. Before applying a radio frequency pulse, you have to know something, that these protons, okay, causing magnetization in the Z direction, which is represented by this yellow arrow, okay. On applying a radio frequency pulse, what will be happening? The protons here will be converted from Z direction to the XY direction, will be in excited state, and this magnetization, which is in Z direction, will be reduced, as you see, okay. And appear another magnetization in XY direction is called transverse magnetization. This magnetization, which is in Z direction, is called longitudinal magnetization. So the protons which appear due to the protons in Z direction is longitudinal magnetization. On applying radio frequency pulse with the same frequency of protons, the proton acquires this radio frequency pulse. It's easy because all of them have the same frequency, so the protons be excited in the XY direction, so the longitudinal magnetization decay, okay, longitudinal magnetization reduce to reach here 0, and another magnetization appear in XY direction, which is called transversal magnetization, or MXY, and the longitudinal magnetization is called MZ, okay. So now after applying, you will find the protons now become in phase. You see the protons now here out of phase, dephased, but here in phase, and the longitudinal magnetization reduced, and another arrow appear here in XY direction, which is the net magnetization of protons in XY direction, okay, and the precession in another direction in XY direction, as you see, okay. This transverse magnetization appear after applying radio frequency pulse, and longitudinal magnetization decrease after radio frequency pulse, okay. After applying radio frequency pulse, longitudinal magnetization here decrease, and appear another magnetization in XY direction, which is called transversal magnetization. So now the magnetization in XY direction moving in this circular path in XY direction and inducing current, because it move in a coil, or in a coil, inducing electrical signal. Here we can record this signal and transform it to image and transform it to EG. This is the main idea of magnetic resonance imaging. Let us talk in details, okay, about this. We will talk about spinlet relaxation, or T1 recovery, or spin relaxation, or T2 recovery, okay. Spinlet relaxation or T1 recovery, we will be interested in longitudinal magnetization, but spin relaxation or T2 decay, we will we will concern with transverse magnetization. What this happen after we switch off the radio frequency pulse? After we apply the radio frequency pulse, already transverse magnetization appear. But after we switch off the radio frequency pulse, the source of radio frequency pulse coming from outside, what will happen? Let us see together. Okay, here talk about spin lattice relaxation. This is the magnetization in the direction as you see here before 90-degree pulse MZ. Here the longitudinal magnetization is 100%. So after 90-degree pulse, what happened to MZ? MZ decreased to zero. So MZ slowly recover. Okay, slowly recover when we switch off the source of radio frequency pulse, we will find that MZ start to recover to reach to 63% of each of MZ. MZ is 100%. When the magnetization here reach to the time taken to reach 63 of 63% of MZ, this is time is called T1 constant. So the time taken to reach 60% of MZ is called T1 constant. After another time we reach to 100%. MZ continue to recover until it reach its starting value of 100%. Okay, so this is what this is called T1 constant. So the T1 constant is the time taken to reach the time taken by the longitudinal magnetization or MZ to recover to 60% of MZ value of longitudinal magnetization. Okay, so now after we switch off radio frequency pulse, what will happen? You see, this is longitudinal magnetization come up again. Longitudinal magnetization now reach 100%. Again, we switch off the radio frequency pulse. This is the transverse magnetization or the longitudinal magnetization is zero. Okay, increase to reach 100%. Okay, the time taken to reach 63% of the longitudinal magnetization, this time is called T1 relaxation time or T1 constant. This is the time, and this is the longitudinal magnetization on the y-axis. 63%, 100% is time 500, 1000, 1500, and so on. Millisecond takes around takes in millisecond. Okay, so the time taken to reach 63% of longitudinal magnetization, it's called T1 constant. Okay, so now not all materials, not all components, not all tissues inside our bodies recover or reach to 63% of longitudinal magnetization at the same time. You will find that some material like fat reaches this 60% in short time, but water takes longer time to reach, and CCF take long time, and you will find differentiation between different tissues inside our bodies in recovery of longitudinal magnetization. That happens because the protons here, when diffusing, lost the radio frequency pulse or lost the acquired energy or acquired radio frequency pulse to the lattice. That means the environment around it. That's why that's the reason why I'm calling this spin lattice relaxation. Spin lattice relaxation. That means the protons here lost the energy or the acquired radio frequency pulse to the environment or to the lattice. Okay, so there are different tissues with different T1 constant, like fat and protein and water, long T1 but short T1. That means time constant 63%, time taken to reach 63% of MZ. So fat and protein is very fast, and water is longer, and bone and calcium very long. Okay, that's the reason why you will find, if you want to go in details to know how to or to understand what's the reason why fat and the protein losing the signal very fast, and water losing the signal very slow, you will find that fat and water moving slowly, and sometimes you will find dense materials and sometimes you will find in fat double bond, which enable fat to lose the energy very fast, but water particles moving very fast. So it's not easy to lose the energy or to lose the radio frequency pulse to the lattice due to the higher speed of molecules of water. Okay, that's the reason why you will find fat, which is represented by fast food, okay, short T1, and long drink you take more time to drink, so water cause long T1. So you water longer T1, but fat is short T1, takes short time to reach to 63% of MZ. Okay, this we talked about the longitudinal magnetization or spin lattice relaxation. Okay, but to give another example here to understand very well, we will talk about fat and water here, all of them in Z direction, and two tissues, two different tissues, fat and water, the MZ here or longitudinal magnetization in Z axis. After applying 90-degree radio frequency pulse, what will happen to the fat and water? Fat and water magnetization will be in the XY excited. Here the protons acquire the energy and will be excited in 90 degree. It is representing the tilting angle or flip angle, the angle which the protons move to, or the angle which causing flipping the proton to. Okay, 90 degrees, so the protons will be in 90 degree, so in XY direction. So now fat and the magnetization coming from fat and the magnetization coming from water the same. Okay, because fat and water now in XY direction. So after certain time, after we switch off the radio frequency pulse, what will happen? We will find that fat is very fast in recovery and water takes long time. So the fat very fast to recovery. So the magnetization of fat here is higher than the magnetization coming from water. So if we want to record the signal coming out from fat or coming out from water in this time, we'll find difference in the signal because the magnetization here for fat is higher than the magnetization coming out from water. Okay, so you will find difference in the signal coming out. Okay, the signal coming out from higher magnetization will be higher signal, lower magnetization will be low signal. Okay, so the higher magnetization here, because we are here the recovery of T1 or recovery of MZ here is higher in fat, and the recovery here is lower in water. So the T1 or MZ here giving higher signal than water. So this signal coming from fat will be represented by bright signal, okay, because it's higher intensity, but the signal coming from water will be low intensity, which is dark. This is the sequence of T1 weighted image. T1 means that we depend on imaging T1 relaxation. We depend on imaging longitudinal magnetization here. So T1 weighted image. That's the reason why T1 sequence depends on imaging of T1 magnetization or longitudinal magnetization. So the fat here appear very bright, more than water, which is dark. This is the T1 sequence. But I want you to remember something. You can differentiate between the signal coming out from fat and water and the main magnetization, which is represented by the main magnetic field. You remember, you can discriminate or you can differentiate between the magnetization of protons and the magnetization in of the main magnetic field, because all of them in the same direction, Z direction. That's the reason why we applying here second 90-degree pulse. Second 90-degree pulse causing the fat will be excited again, okay, to reach at certain value, and water to be another value. But each component here, or each one, fat or water, will be excited with its force, with its power, with its magnetization. So but you will find here that fat has a higher magnetization than water. So fat here giving you, but now you succeed, we success in discrimination between the magnetization of protons and the magnetization of the main magnetic field, okay, after applying second 90-degree pulse. So now you can record the signal very easy, and you will find the signal coming out from fat is brighter than the signal coming out from water. This is the T1 weighted image or T1 sequence. This is the main idea of T1 sequence. Here in T1 sequence we record, or we are using the longitudinal magnetization of different tissues, and we are using the difference in recovery time of recovery of different tissues, okay, to discriminate between or to differentiate between different tissues of our pods, okay. If we represent the curve of longitudinal magnetization, as you see, here's the longitudinal magnetization value or percent, here is time, you will find that fat recoveries. This is after we switch off the radio frequency bulbs, that fat is recovery very fast, as you see, reach to 100%, but water taking longer time to reach to 100%. So now fat takes time, okay, short time, but water takes long time. As we said before, that fat fast food, while water is takes long time to drink after we eat, after we are eating fast food, okay. So water long T1, okay, and fat is short T1, takes short time, or takes short relaxation time to be recovered to 60% of longitudinal magnetization, okay. So you'll find this is the image of T1. You'll find here is fat is more bright, and you'll find CSF, because it's fluid, you'll find it is dark, okay. This is the differentiation between fat and CSF, okay, and so on, all tissues inside the image, according to the T1 constant, according to the recovery time, you can differentiate between it, okay. Second, we will talk about spin spin relaxation, which is related to the transverse magnetization, or MXY. So now let us talk about the transverse magnetization. As you see here, the transverse magnetization, and the protons here become in phase, as you see, okay. But after we switch off the radio frequency pulse, which is coming from the radio frequency coil, what will happen to the protons? The proton itself dephased at a certain time, dephase. As you see here, the protons dephasing, dephase, okay. So this dephasing is called spin relaxation. This dephasing causing loss of signal, causing loss of magnetization, So the transverse magnetization decay due to the spin relaxation, or after certain time you will find that protons here, each proton in a certain direction, you will find another proton at another direction, opposite direction, so neglect each other. So the total magnetization here will be reduced, so the transverse magnetization reduced till reach 0. So you have to know something very important here, that transverse magnetization and longitudinal magnetization, two separate processes, not depend on each other, okay. Two separate processes. Transverse magnetization depends on spin relaxation, but longitudinal magnetization depends on spin lattice relaxation, okay. Transverse magnetization appear after switching off the radio frequency pulse come from outside. We'll find that protons here began to dephase, okay, and after certain time we'll find the proton in a certain direction, another proton in opposite direction, so neglect each other, okay. So when we want to draw the curve here, you will find radio frequency pulse, the net magnetization will be in y-axis, okay, which is called MXY, which is will form transverse magnetization, and this is excitation process, okay. Here the protons here in longitudinal magnetization were out of phase, but after excitation becomes in phase. As you see, look at here out of phase, here after excitation become in phase again, okay. So the transverse magnetization will move in XY direction, okay. Now after we switch off the radio frequency pulse, you see, we switch off the radio frequency pulse, protons start to dephase, as you see here, okay, till a certain dephasing process. This is called spin relaxation. It's called spin relaxation, okay. This is losing the magnetization, okay, losing the magnetization. If we record the signal at this time, okay, for different tissues, if we record the signal at this time for different tissues, we'll find that certain tissue like fat, the phasing of protons inside the fat will be faster than the protons of water, because fat takes short time to dephase, protons inside the fat take short time to decay, but water takes longer time to decay. So you can differentiate between the magnetization coming out from the fat and the magnetization coming out from water, so you can differentiate between them. As we see here, that this is a signal which is coming out. Okay, we represent signal like sine wave. As you see here, that the protons is the magnetization here, okay, is higher. This is after applying radio frequency pulse. Here, after we switch off the radio frequency pulse, we will find the proton, the magnetization spin in other direction, so the curve, the sine wave decay. So here, after dephasing of protons, the magnetization mxy reduced, so the curve starts, the peak of the curve here, not like before, and again, and so on. You will find this is called free induction decay. This process is called free induction decay. This is called the free induction decay. This is depend on spin relaxation. Spin relaxation. We record this signal if we want to record T2 image, T2 weighted image. How come? Okay, we'll see together. Here mxy. Okay, after applying radio frequency, before 90-degree pulse, mxy is 0%. Okay, after 90-degree pulse, mxy is 100%. Okay, so we switch off the radio frequency pulse here. What will happen? The mxy decay till reach 37% of mxy. This time is called, the time taken to reach 37% of mxy, it's called T2 constant, which is transverse magnetization. Now transverse magnetization decay to 37% of mxy. This is called T2 constant. So mxy continues to decay until it reaches its starting value again, 0%. Okay, so we have different time constant, different T2 times constants with different tissues. We have different T2 constant with different tissues. Okay, you will find that bone, calcium, metal, short T2. Okay, the local variation of magnetic field is greatest in solids and molecules that are rigid. Okay, fat, long T2, but not longer than water. That's the reason why I said before that it's short. Water is a very long T2, because the lighter molecules are in rapid thermal motion that moves out the local field, producing a longer T2. Okay, so now you will find the protons moving in, this is on applying the external magnetic field, as I said before. Process again. This is a precession frequency, 2 Tesla. You will find, I'm just reminding you here that the Larmor frequency increase 1 Tesla, 42. When applying a higher, this is Larmor equation or precession frequency. So now we'll give you an example what will be happen if you want after applying radio frequency pulse, that the protons here, okay, becomes in phase and appear here transverse magnetization in xy direction. Okay, after we switch off, okay, this is a process of excitation process. Now 90-degree pulse here. Okay, the mxy moving in xy. All this I told you before, but I'm just reminding you now. Okay, moving again. Okay, we talked before about fat and water. Okay, so now this is T1 constant and T2 constant. Now we understand well what's the difference between T1 constant and T2 constant. T1 constant is represented is related to longitudinal magnetization, while T2 constant is related to transverse magnetization. T1 constant, which is time taken to recover of longitudinal magnetization of a tissue to 63% of longitudinal magnetization, or MZ, while T2 is the time taken of certain tissue to decay to 37% of MXY. Okay, so we'll find fat is 250 millisecond. Takes fat here takes around 250 milliseconds to reach 63%, while in T2, okay, which is spin relaxation, while T1 is spin lattice relaxation, takes around, for fat, takes around 80 milliseconds to decay to 37% of MXY, kidney, white matter. When we differentiate between water, you will find water very long T1 constant and very long T2 constant. Okay, if we record this signal to get the image of T2 weighted image, okay, for fat and water, here is T1. This is the curve of MXY after we switch off the radio frequency pulse. What will happen? You will find that fat here takes short time to reach to decay for MXY. Okay, and this is with time, and while for water take longer time. So you can differentiate between longer T2 and shorter T2 tissues. Okay, here is a poor contrast between, if we record the signal at this time, you will get poor contrast, but if you record the signal here, you will get a good contrast between two different tissues, because here the magnetization of water, for instance, is higher than the magnetization of fat. So the water will give you bright signal, while fat will give you dark, less bright signal than water. Okay, so that's the reason why we have to select the time of record of the signal. Okay, the time of record of the signal. So now the time of record of the signal in MXY or T2, okay, T2 sequence, is important to get better contrast. If you choose, or if you select here short TE, you will get poor contrast between the tissues. You can differentiate very well between different tissues, but here if you select long TE, you can get a good contrast between different tissues like water and fat. Okay, it's a very important parameter for which is responsible for the contrast. The image contrast in T2 weighted image is TE, while in T1 weighted image, which parameter is responsible for the image contrast is TR. Here you will find here that tissue with long T1, okay, and tissue here with short T1 takes short time to recover, okay, like fat, and here takes long time to recover like water. Okay, here the time here, if we select TR, repetition time. What's the meaning of repetition time? The time of repeating the signal. If we select the repetition time short, so we will get good contrast, but if we select longer repetition time, it will cause poor contrast. I know now that you are confused and you want to understand this very well. Okay, let us go back here and understand. For T1 weighted image, we have fat and water, okay, and all of them in Z, fat and water in Z axis after applying 90-degree pulse. What will happen for fat and water? Magnetization coming out from fat and magnetization coming out from water are equal together, okay, in XY. So now we wait for certain time. Why are we waiting for certain time? For relaxation of for recovery of longitudinal magnetization axis for water and fat. Okay, for now fat will be higher than water. Okay, so if we record the signal at this time, so you can differentiate between the signal coming out from fat and water and the main magnetic field. Okay, so we have to give another 90-degree radio frequency pulse, which causing the fat and water magnetization to be flipped in XY direction again, to differentiate between magnetization coming out from protons and the magnetization coming out from the main magnetic field. Okay, so the time taken between first 90-degree pulse and second 90-degree pulse is called TR, the repetition time, because we are repeating the radio frequency pulse here. Here we are giving 90-degree pulse, and after some certain time we are giving another 90-degree pulse. This is called repetition time. The repetition time here is very important. If we select long repetition time, we take longer time. If we take longer time, okay, before applying the second 90-degree pulse, the fat and water will be fully recovered, and reach 100%. So you can differentiate. If we apply the second pulse after a long time, so the protons, so the fat and water, okay, will have the same value like before. So we are repeating this one again, okay. So if we take long time to apply the second pulse, fat and water will be fully recovered. So you want to differentiate between them, so you have to make a difference in magnetization between them, so you have not to take long time. So the reason why TR, which is the repetition time between the first pulse and second pulse, is short in T1 weighted image, like here. If we select short TR, so you have good contrast between water and fat, but here longer TR is poor contrast between, you will get poor contrast between fat and water. So TR is very important parameter for image contrast in T2 weighted image, while in T1 in T2 here in T1 sorry here TR is very important parameter for T1 weighted image, but here is very important parameter for T2 weighted image. If we select short TE, okay, you will get poor contrast image, but long TE represented by recording time, okay, recording time of recording, good contrast of image, okay. So it's very important to understand this very well. At the beginning, all protons in XY for of fat water still have magnetization in equal. After a certain time, you will find that fat takes short time to decay, but water takes long time to decay. So there is a difference in magnetization between fat and between water and the fat. So when you record the signal at this time, you will the higher magnetization will give you more bright signal like water, but while the less magnetization of like fat will give you less signal like fat, okay. So TE is a very important parameter for T2 weighted image, okay. Here T2 weighted image, you'll find here this CCF is bright, okay, and while fat here, you will find fat here is less bright, okay. This is the shape of a pulse sequence. You will find here TR and TR, okay. This is the repetition, the first pulse, second pulse, third pulse, and so on. Here is the time of recording, TE, okay. So we are repeating here the first pulse, second pulse, third pulse, and so on, okay, because we are repeating this process not only one time, but we are repeating it a lot of times, okay, to get not only one slice or one image, but we are getting a lot of image, maybe 20 image or 30 image for one organ. So it's important to repeat it. So repetition time TR, but the recording is the time of recording is the signal. Here for T1, the recovery, fat recovering very fast, water takes long time. So if we record at short TR, you will get here for fat, you will get good contrast between fat and water, but if we select long TR, you will get poor contrast between fat and water. That's the reason why we are using short TR for T1 weighted image, and as such short TE as well, okay. But here for T2, you will find the decay of water is very long, but the decay of fat is very fast. So the difference here, or the contrast here, or the contrast here between wet and water is very poor. So at short TE, okay, your recording is the signal will be very poor. So we are using long TE, long recording time, so the difference here between water and fat will be very high, so we'll get higher image contrast. So as we are using long TE, so that's the reason why we are using long TR as well. But TE is important for T2 sequence, but TR is important for T1 sequence. Okay, so for T1 we are using short TR, short TE, but for T2 we are using long TR and long TE and long TE. Okay, this is the difference between T1 sequence and T2 sequence. T1 sequence, as I said before, it is spin lattice relaxation, and we are recording here coming out from longitudinal magnetization, while in T2 sequence we are recording the signal coming out from transversal magnetization. Transversal magnetization, or the decay of the transversal magnetization, is due to spin relaxation, but the recovery of MZ, which is longitudinal magnetization, is due to spin lattice relaxation. Okay, here you will find this is T2 image. CCF is bright, okay, because it's very long in decay, CCF here, and fat takes short time. Okay, so TE is long, is very important in T2 sequence to get difference between CCF and fat. Okay, okay, this is the T2 curve. Okay, T2 curve, here is the percentage of magnetization of T2. This is the decay curve. Okay, this is the curve, is called T2 star. Why? Because the protons, as I said before, the protons dephase in XY direction, dephasing after a certain time, dephasing. This dephasing is due to field inhomogeneity and susceptibility effect. Susceptibility effect. Field inhomogeneity, you will find the field of magnetic field is not homogeneous, causing the protons to dephase. After a certain time will be in different positions, so the protons neglect the proton magnetization neglect each other, or the magnetization loss of protons in XY. So now I want to get the signal coming out from tissue itself, not from the field inhomogeneity or the environment around the protons in XY direction. Sometimes the tissues around the protons in XY direction causing a changing in the magnetic field. So the protons, each proton will acquire magnetization, different magnetization coming out from the field, coming out from the environment. That cause with time to the proton get higher magnetization, will process more faster than the proton that get less magnetization from environment. That causing the proton to dephase very fast, dephase very fast. Okay, that cause losing the magnetization very fast. But if I want to get the image, okay, due to tissue characteristics itself, like fat and water, like components or pathology of different components or different tissues inside our bodies, okay, we will do another thing. We will give a radio frequency pulse, which is called 180 degree pulse. 180 degree pulse cause rephasing the protons again. To remove the effect of field inhomogeneity and susceptibility effect. So this is happen in T2 image. So the T2 image depends on tissue characteristics. But if I want to get the image depending on field inhomogeneity or susceptibility effects, okay, you will get the image of T2 star without applying 180 degree pulse, as you see here. Okay, I wanted to explain it to you. Okay, here, yes, here, this is 42 image. We applying 90 degrees, so the protons here in XY dephasing is due to spin relaxation. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll apply 180 degree. The protons, okay, will be in XY direction. So I want to rephase the proton again. I'll app will rephase again. That's removing the effect of inhomogeneity of the magnetic field, inhomogeneity or stability effect, and after that we record the signal again. Here's the protons in z direction. We applying 90-degree excitation happen. MXY appear now. Protons start to dephase due to spin relaxation or magnetic field inhomogeneity. We applying 180-degree, making the protons rephase again, and we record the signal. This process happen 42 weighted image, but if we want to get the image and we want to depend only the magnetic field inhomogeneity or stability effect, we will remove 180-degree pulse. We will remove 180-degree pulse and get the signal when the proton dephase. Okay, so it's called T2 star sequence, or gradient sequence, okay. So now this is the proton, as you see, okay, dephasing the proton with time. As you see, each proton, this proton will be here at time, and another proton at a certain time, and so on, in different times, come to be out of phase. Okay, here after applying 180-degree, the protons rephase again. You will find this proton and all of them becomes rephase again, and the magnetization would be higher at this time. So the T2 image here, depending on applying a 90-degree pulse, after that we will apply 180-degree radio frequency pulse, causing a refocusing of protons again, or rephasing the proton again, okay, in XY direction. This is called spin echo process. Here, this curve is the first curve without applying 180-degree. It's called T2 star, or the free induction decay. As I said before, that the protons dephase. Here we applying 90-degree radio frequency pulse. Okay, the protons here, the MXY is higher, start to dephase, proton dephasing, and to reach zero. This is due to spin relaxation, dephasing, magnetic field inhomogeneity, stability effect, or due to the environment. Okay, if I want to remove the effect of magnetic field inhomogeneity or stability effect, I'll apply 180-degree radio frequency pulse that cause rephasing the protons again and increasing the magnetization again of protons, and enhances the signal coming out. Okay, enhances the signal, and signal here coming out, and we will transfer this signal to get an image. Okay, but for T1 this is called spin echo process. But for T1 weighted image, here we are applying a 90-degree radio frequency pulse, as I said before. So the fat, this saturation pulse, as I said before, as it is called saturation pulse. So we are talking about now longitudinal magnetization, or T1. Because the fat takes short time to recover, so short T1, but water take longer time to recover. So at certain time, when there is a difference between the magnetization coming out from fat and water, from short T1 and long T1, we will apply second radio frequency pulse, which is responsible for excitation. And now we will get the image. Okay, we will get the image with this difference in magnetization, because the protons, as I said before, that here 90-degree pulse, this is the saturation pulse at first, and second 90-degree pulse, which is responsible for excitation, okay, to get the difference between fat and water. Okay, so this is the longitudinal phase or spin echo sequence. Okay, we are using here again short TR, not long TR. If we are using here long TR, so the protons of fat and water will be fully recovered to reach 100%. So sequence will be useless. We will apply second pulse. The proton fat will be again with the will be again equal in XY direction. So it's useless. But we have to select short TR to get better contrast between fat and water. Okay. The proton density sequence. Proton density sequence is very important, but it depends on the number of proton in different tissues. Each tissue, each component inside our bodies contain different number of protons. Water has different number of water than fats and bone and so on. Okay, so if we want to get the image depending on the number of protons, so we have to select TR and TE, TR and TE, okay, to neglect the effect of longitudinal magnetization and transversal magnetization. Okay, so if we select here long TR, so if we select the long TR, so the magnetization of, for instance, of water and fat will be equal here, which is coming from longitudinal magnetization. So we select the long TR, and if we select long TE, so we will get difference in T2 magnetization or transversal magnetization. So we have to select short TE. Why? Because there is a small difference in transversal magnetization between water and fat. So in proton density sequence, you must remove the effect of transversal magnetization and longitudinal magnetization. But here in proton density sequence, we will depend on number of protons. So we will select long TR, okay, so the effect of this is T1 sequence and this is T2 sequence. So here if we select long TR, okay, after we applying radio frequency pulse, the magnetization, longitudinal magnetization, okay, after we applying radio frequency pulse, if we talk about after we switch off the longitudinal magnetization here for short T1, long T1, recover again, okay, to reach this value. At this value, okay, I'll select the repeating of signal, because at this value there is no difference between long T1 and short T1, okay. So I'll apply at certain time where short TE and long TR. Short TE to remove the effect of transversal magnetization, because at short TE, this is a curve of T2 curve. At short TE, you will find the transversal magnetization effect is very low, or the difference between the difference between water and fat or tissues here in at short TE. If I want to record the signal at short TE, so the difference here is low, is poor. But here at long TR, here at very long TR, if we wait for very long time for T1 sequence, so the difference will be very low. So we will select the parameter which enable us to get the image depending on the number of protons only. So we will get TE, short TE and long TR. So now radio frequency pulse. After that we will wait long time to give another radio frequency pulse. So the repetition time will be high, will be long. The repetition time here will be high, will be long, okay, and TE magnetization will be very short, okay, to remove the effect of transversal magnetization, where there is no difference between the signal coming out from fat and water. And at long TR, there is no difference between the signal coming out from fat and water for longitudinal magnetization. So the signal only, or the difference in the signal here will depends only on the proton density. Okay, so if you want to record the signal at any time, you will get signal coming out from transverse magnetization and longitudinal magnetization and the proton density as well. Yes, because the proton density causing it to give you signal due to the magnetization of proton, which depends on the number of protons, and transversal magnetization will give you a signal depend on spin relaxation, and longitudinal magnetization will give you a signal depend on spin lattice relaxation. So how can I differentiate as a machine between all these signals coming out? You will differentiate the signal you are detecting all the signal, but you depends on the difference in signals, not on the signal itself. If two different tissue giving you different signal, so there is a difference in the signal, so now you can get difference in signal, so you can get difference in image, different in brightness, difference in grayscale, so you will get difference in the image. But if the signal coming out from different tissue with the same value, with no difference, so you will represent it with the same grayscale, with the same color. So that's the reason why we are selecting TR and TE is specific for each sequence. We are selecting long TR, long TE for T2 sequence, and we are selecting short TR and short TE for T1 sequence, and we are selecting long TR and short TE for proton density sequence. So you have to select specific TR parameters of TR and TE for a specific sequence you need. Selecting TR and TE is very important to remove or to ignore the effect of certain magnetization. If we select, as I said before, long TR, so you will neglect or you will remove the effect of longitudinal magnetization. If you select short TE, you will neglect the effect of transverse magnetization. So TE is very important for transverse magnetization, image contrast, for T2 image contrast, and TR is very important for T1 weighted image, for to image which depends on longitudinal magnetization or the difference in longitudinal magnetization. But for proton density, we have to remove the effect or remove the signal difference coming out from longitudinal magnetization and remove the signal difference coming out from the transversal magnetization or T2. So we have to select long TR, okay, to remove the signal difference coming out from longitudinal magnetization or T1 weighted image or T1 constant, and select short TE to remove the effect of to remove the signal difference coming out from transversal magnetization, and the signal only or the signal difference here will depend only the number of protons, So I think I want to continue to talk about K-space and image reconstruction, but I think it's more than enough. Now it's a good time to stop now, okay? This is a sequence of, again, 90 degree, 180. When you see 180 degree, you have to remember this is T2 sequence. Why we are applying 180 degree? To refocus the protons again, or to rephase the protons again in the XY direction, okay? Okay, this is yes, this is long this is the proton density image, and this is T1 image, and this is T2 image. Here we are using for short TR and short TE. You will find here CCF, as you see, is dark, which is low, long T1 constant, while here is CCF in T2 sequence is bright, okay, which is long T2 sequence, long T2 constant, but giving you brighter signal because it's higher magnetization than fat, okay, but here the fat here is bright and the fat here is less bright than the CSF, okay. Here in T1 sequence we are using short ER, short E, and for T2 sequence we are using long TR, long TE. Here the image depends on the number of protons in different tissues. This is called the proton density image. Proton density image, okay. Okay, I'll stop here, and I think the next session I'll talk about special encoding in MRI. Okay, thank you very much. If you have any question, please leave your comment downside.